All right, let's talk about steel. You know, the stuff that builds our world. But we're not going to talk about skyscrapers or bridges. We're going to dive deep, way down to the microscopic level to uncover a hidden weakness, an invisible flaw that can make even the strongest steel fail. So picture this. You've got a brand new, massive coil of steel, fresh from the mill, weighing tons. How is it possible that a flaw so small you can't even see it is hiding inside, just waiting to cause a catastrophic failure?
Well, the culprit has a name, a non-metallic inclusion. Basically, it's a tiny little impurity, a foreign particle that gets trapped inside the steel as it's being made. The best way to think about it, it's like a tiny, invisible crack in your car's windshield. It might seem like nothing until it spreads.
And here's the crazy part. These things make up a tiny, tiny fraction of the steel's total volume. We're talking less than 0.1%. It's almost nothing. But, and this is a huge but, that tiny fraction can completely wreck the steel's most important qualities. It can destroy its strength, its toughness, and its ability to be shaped into the parts we rely on every single day. So, what are these tiny terrors really? Well, it turns out they're not all created equal. They actually have different origins. Let's take a look at the inclusion family tree. Okay, so inclusions really fall into two main families. First, you've got endogenous ones. Think of these as natural byproducts. They're formed by chemical reactions happening inside the molten steel. They're pretty much an unavoidable part of the deal. Then you have the exogenous ones. These are the accidents, foreign invaders, like tiny bits of slag or ceramics from the furnace that get trapped in the mix. But here's the twist. While it's good to know where they come from, their origin story isn't what makes them a threat. What really matters, what makes them truly dangerous, is their shape. We can actually break them down almost like characters in an old Western movie. You've got the ugly. These are alumina clusters. They're sharp, jagged, and brittle, like little daggers inside the steel. Then you have the bad, the sulfides. During processing, they get stretched out into these long, thin lines that create weak spots. And finally, you have the good. These are modified oxides. They're smooth, they're round, and for the most part, they're totally harmless. And don't just take my word for it. The research is clear. It's the inclusion's morphology. That's just a fancy word for its size, shape, and how it deforms that overwhelmingly determines its effect on the final steel. So yeah, it really is all about the geometry. Okay, so if shape is everything, how do these different shapes even form? Well, to understand that, we have to take a trip right into the heart of a steel mill, a journey through fire. So, here's the super simplified path. It all starts with primary steelmaking, melting everything down. Then the molten steel goes into a giant bucket called a ladle for refining and fine-tuning. After that, it gets cast into a solid shape. And finally, it's rolled while it's still red hot into the coils you see. Now here's the really tricky part. Inclusions don't just pop up at one point. Oh no. They can be born, they can change shape, or they can get trapped at pretty much every single step of this intense, fiery journey. But in this constant battle, there is one stage that is absolutely key. The source material tells us the ladle is arguably the most critical stage for controlling what these inclusions look like. This is where the real fight happens. So if these things are so dangerous and they're forming all over the place, how do steelmakers possibly win? Well, this brings us to the really cool part of the story, engineering the perfect steel. See, modern steelmaking isn't just about trying to scrub all the impurities out. That's old thinking. Today, it's about a much smarter philosophy called inclusion engineering. The goal isn't just to remove them, it's to actively control their size, their shape, and where they end up, basically turning them into something that does no harm. Let's look at this in action. Before any treatment, you have our main villain, that sharp, nasty alumina. It causes all sorts of problems, but after you treat the steel with calcium, that alumina transforms into something new. Calcium aluminate, and this new stuff solidifies into a hard but perfectly harmless little sphere. So how does this chemical magic trick actually work? It's really elegant. Step 1, you inject calcium right into the molten steel. Step 2, the calcium goes on a search and destroy mission, finding those sharp alumina inclusions and transforming them chemically. Step 3, this reaction creates tiny liquid droplets of a whole new compound. And finally, step 4, as the steel cools, those droplets just solidify into perfect, smooth little spheres. And here's the payoff. Changing from that angular, sharp-edged shape to a smooth, spherical one drastically reduces the stress, rendering it largely benign. The threat has neutralized. You haven't removed the enemy, you've just disarmed it. It's brilliant. The science is amazing, for sure. But how do they know for a fact that it worked? That brings us to our final stop, the final quality check. You've got two main ways to check your work. First is what they call the gold standard, destructive lab analysis. You literally cut a piece of steel out and stick it under a powerful microscope for a super precise look. The other way is non-destructive inspection, which uses cool tech like ultrasonics to scan huge amounts of steel right on the production line without hurting it. And this non-destructive tech is like a whole team of high-tech inspectors. Ultrasonics use sound waves to find deep internal flaws, kind of like sonar. Magnetic particle testing can spot cracks on or near the surface by finding leaks in a magnetic field. And eddy current testing uses electricity to find surface flaws at incredible speeds. Each tool has its own very specific job. But when you really want the full story, you go back to the lab. Because, as the source material says, under a powerful electron microscope, every inclusion tells the story of its journey, its shape, its chemistry. It's like a tiny fingerprint that reveals exactly what happened to it inside that furnace. So, the next time you see a bridge, a car, or a skyscraper, just remember this. As our world demands stronger and lighter materials, the quest for perfect steel isn't about brute force. It's really a story of mastering its tiniest, most invisible imperfections.